I'm just kidding. Okay, so this here kind of looks like an apostrophe. This is what we call f prime. And that's how we call the derivative of something. F prime of x is the same thing as the tangent slope, or the slope of a curve at a point. Okay, we're just calling it derivative now. So how do we know if it has a derivative, if f prime exists? We say that it is differentiable. Okay, now we did this a little bit in our previous lesson. How do we know that it has a slope at a specific point? It's got to have the same slope from the left and the same slope from the right. So that's what it needs in order to be differentiable. It's all the same thing, we're just calling it different terms. And then if we have a function that's differentiable at every point of its domain, it's a differentiable function. Okay, so for example, I can give you an example of a differentiable function would be f of x equals x squared. That's just a plain old parabola, okay? I can find the slope at every single point, okay, and it'll be the same. A non-example would be f of x equals the absolute value of x. Why does that not work? Well, it can be negative, but it's a piecewise function. What happens at 0 or when? Yeah, there's a sharp corner, so it has a different slope from, right? You picture our V shape has a -1 slope until we get to 0, and then it has a +1 slope. So since those don't match up, this is a non-differentiable function. Okay. All right, let's look at some notation. I just introduced you to f prime of x. That's one form, okay, to describe it. If I just give you y equals x squared, we can just write y prime. Then we have some other notation. We'll see dy dx. This means the derivative of y with respect to x. Okay, now remember what I just said about derivative. What was it equal to? It was equal to slope of the tangent. What's slope? Just think back to Algebra 1. What's the formula for slope?
Rise over run.
Rise over run, y2 minus, so the change in y, take a look, dy, d delta, right? Same thing, delta y over delta x, change in y over change in x. So that's where we get that notation from. This is the same thing, just with a function, right? So df dx, derivative of f with respect to x. And then the last one is just that sometimes I'll use that notation showing I want to take the derivative. So d dx means I want to take the derivative of f of x. So the derivative of f of x. Okay, let's do x cubed. We've already done this. We're going to use that old formula, and then I'm going to give you a new one that you're going to like a lot better. I promise. I wouldn't lie to you. Okay. We want to find f prime of x. So we're going to just write that out. And we have the limit as h approaches 0. Our function is x cubed. Okay, and we don't know what point. We want, basically at the end, we're going to have something in terms of x. Okay, so what's that going to be? X plus h cubed minus x cubed all over h. Okay, does anybody remember how to cube a binomial?
I think you just take one of them out and then you multiply it by the square of it.
You could do that. You could do that.
The
Pascal's triangle, if you remember that.
The coefficients are like 1, 3, 3.
Do you remember it?
Oh yeah.
That's
Pascal's theorem I saw for.
I mean, that's one use for it, Scotty, but okay. Do you remember it? What is it?
One and then one.
Okay, here, I'll write it on the board. Okay, so 1, 1, 1,
1, 2,
2, 1, 3, 3, 1. So the 3's are the coefficients of the middle two terms? Okay. Now, if you didn't know that, could you just multiply x plus h times x plus h times x plus h? It would take a little bit of time. Of course, we like shortcuts, so if we remember it, it's great. Okay, so it's going to be x cubed plus 3x squared h plus 3x h squared. Does that look familiar? Okay, and then plus, what's the last term? H cubed minus x cubed. Okay, let's see, what's going to cancel here? The x cubes, right? Okay, can I just, I saw on a lot of people's papers, they just started crossing off h's. And although if you can do that and you could do that correctly, great, but I saw so many little mistakes. I highly, highly encourage you to just factor out the h, okay? Because I saw so many little mistakes there. So I get 3x squared plus 3x h plus h squared. Okay. Again, I know if you're used to, if you feel confident that you can just start crossing off h's, fine, but there was a lot of little mistakes there. I think it's good to just take that extra step. If you have the time, just do it. Factor out the h. Now what? Now we can substitute in h equals 0. Well, that means these two terms will go away. We just get, there we go. So that means f prime of x is equal to 3x squared. Perfect. What does that mean from a geometric standpoint? Well, yeah, Andrew.
The slope at a given point.
Yeah, so that means like right here's like a real fast sketch of x cubed. That means at any point I can find the slope according to that formula. So I could say when x equals 2, what's that slope going to be? 12. Right? Okay. So I just want to make that connection so that we remember it's still referring to the slope at a point. We're just calling it the derivative. All right, here's our alternate definition of the derivative at a point. This one is generally much easier to work with, okay? Why? We don't have to deal with that whole x plus h business, okay? So this time, we're going to take the function and we're going to subtract f of a, right? If we know the value of a, we'll plug that in. If we don't, then we'll leave a in our answer. Over x minus a. Why is that the same thing as the previous one? Look at it. What is it? What do we notice? It's the same as the average. Isn't that still slope? Is this change in y over change in x? And what's that mean? X is approaching a. It's getting smaller and smaller and smaller, kind of like the h approaching 0. Same thing, okay? Just a different way to look at it. Kind of nice, huh? Okay. I mean, I think it's nice. Right, so here's our secant slope. So what we're saying, here's a, f of a, here's x, f of x, and we're going to slide that closer and closer and closer so that we can get a tangent slope. Okay, all right, let's try it. We want to find f prime of 2, and we're going to use that definition. I will specify on quizzes or tests which definition I want you to use. Just most from now on, we'll have this one as an option, which is nice. It's less work. Okay. Okay, what are we going to have the limit x approaching what? Okay, what's a in this case? 2. So I'm going to say x approaching 2. Good. What's f of x? Square root of x minus 1. Minus, what's f of a? What happens when I plug in 2? I get 2 minus 1 under the radical. Oh, it just means minus 1. All over x minus 2. Okay. Now, obviously, I cannot substitute x in because what happens in that expression? It would be 0 over 0, something we call indeterminate form. We'll deal with that later, but we can't substitute it in. If just the top was 0 or just the bottom was 0, that's a different case. What do we want to do?
You want to multiply the top and bottom by the square root of x minus 1 plus 1.
Yes, we do. So, square root of x minus 1 plus 1 over square root of x minus 1 plus 1, right? We're multiplying by the conjugate. of that numerator. Why? What do we want to get rid of? We want to get rid of that squared in the top. Am I going to FOIL the bottom? Please do not, right? That's going to make it a crazy mess. Okay, here we go. Now the top, I am going to multiply out because these are two conjugates. And so when I do FOIL, remember I don't have to worry about the outside and the inside. I can just multiply the first and the last, right? Making it a lot easier. So what happens? Square root of x minus 1 times square root of x minus 1? X minus 1. And then minus 1 times a plus 1? Minus 1. Okay, again. Wow, what are we doing outside? Maybe it's just neighbor construction. All right, what do we notice? Remember how we always wanted to cancel that h? Now we always want to cancel the x minus a. Are you okay if I just cancel it like that? Okay, now there's still a 1 in the numerator. Now if I substitute in x equals 2, we're good, right? We don't get 0 over 0, so let's do that. And that's going to give us f prime of 2. So I get 1 over 2. Not too bad, right? Okay. Good. Aiden, you got a question?
Yeah, for the numerator, right, when you FOIL it,
Yeah.
why is it not like 2 root x minus 4? Or minus 2 root x minus 4?
Oh, so whenever you have something of the form a plus b, a minus b, right, it's going to be a squared, right, minus ab plus ab minus b squared. What happens when you have conjugates, the two middle terms? That's what I was saying about FOIL. I was just reminding you that when you do FOIL, right, we set it up this way on purpose so that it works out to this nice expression in the numerator. Yeah, Mayan?
So the f prime of 2 just stands for the derivative.
That means the derivative when x equals 2 equals 1/2, right? Could you graph the function square root of x minus 1? Yeah, so that would just look like that. So they're saying at x equals 2, the slope is 1/2, okay? So we say the derivative when x equals 2 is equal to 1/2, which is the slope of that curve. Yes?
Kind of a weird question, but like when you draw that tangent line on, let's just say a curve like that,
Yeah.
how do you know, like you draw it at the point, but how do you know like how much?
Oh, it's almost like if you were to take a point. Okay, this is not a nice looking ruler, but, right, if I were to take a ruler or a straight line and I just kind of, right, because it would change, right? Here's your tangent line. Here's the tangent. And then if I were to follow the curve, like thinking right in the middle of that ruler is your point of tangency. And it's kind of following along that curve. Does that make sense? Okay. All right, let's try the next one. Do you want to try it? Do you want to do this one on your own or together? You're afraid? Okay, we'll do another one together. Here we go. Now, this is a little different notation. I'm just getting you exposed to different ways to write the same thing. So I want d dx of 3x squared. Okay, I'm going to draw a vertical line, which means evaluated at x equals -1. So this little line here means evaluated at, and then x, or a equals 1, excuse me. Okay. All right, so limit, x approaches what? -1, good. Now, we want f of x. What is our function in this case? The 3x squared. So I'm going to have 3x squared minus, now I want to substitute in -1. What happens when I plug in -1? Minus 3 over x minus a. So that's going to become x plus 1. Good. All right, try it from here. You can do this. You can do factoring. I have faith in you. Okay, I'm going to freeze my screen, so. Isn't this so much fun? Don't laugh, I was serious. Anybody got it yet? Let me see. Oh, good. Okay. God. Good. Did I scare you?
Yeah, you did.
Oh, sorry.
How do you write the answer out? Do you write it out loud? Or would I just keep it like?
Oh, when I wrote it, I just wrote that this time. See? How was it? Did we get -6? Excellent. Okay. No, we didn't? Yes, we did. We did. If you didn't, maybe you made just like a little careless error. Okay. Good. Questions on that definition? Yeah, man.
Is there a way that the answer needs to be written?
Oh, so if you just keep drawing the equal, I'm okay with that. And then circling. I wanted to just, for this one, it's a little bit easier. It's less writing. Maybe I was just getting a little lazy, it's Friday. But I wanted to write it here so that we could relate it back to geometrically what that means. But this is the same thing. What's 3x squared look like? It's a parabola. So at -1, when x equals -1, we have a slope of -6. That sounds about right. Okay. Amit?
Are there different situations where it's like better to use one of the notations, or is it just whichever one they tell you to use?
I would almost always use this one.
Okay.
Unless we are doing left or right-sided derivatives. We'll get to that because you're jumping ahead, but yeah, Mayan.
Would we need to do this without plugging in A?
Yes. So what would that? So let's say I just said at x equals a. Right. So here, you don't need. I mean, you can write it, but what if it said it would go x approaching a of 3x squared minus 3a squared all over x minus a? Can you still factor out a 3?
Yeah.
Can you still factor out x squared minus a squared? And then you'll get x plus a, x minus a. You'd still cancel out that x minus a. And then at the end, you would just get something all in terms of a. Okay, so it works out very nicely. You would end up, in this case, you would end up with the 6a. Just if you wanted to try that on your own, but. Oh, sorry, did you write it? Sorry, Molly, I see. Okay, let's look at the relationship between the graphs of f prime and f. What is f prime again? Derivative. And what's derivative? The slope of the tangent. Okay, here is, it says y, but let's label this. This is my original function, f of x. And let's graph f prime of x. Now, the x values stay exactly the same. Okay, so when I see my graph go from 0 to 5, that means I'm going to have a graph from 0 to 5 on here. It's the y values that are going to change. All right, well, let's take a look. We see from 0 to 1, what is the slope? Like literally, can we count rise over run? From 0 to 1, it looks like it goes up 1, 2, 3 over 1. So that has a slope of 3. And then from 1 to 3, and I'll explain why I included the 0 and not the 1 on the inequality in a minute. Here I'm not going to include it either way. So from 1 to 3, what's my slope? 0. And then from 4 to 5, what's my slope there? Or sorry, I missed 3 to 4. I'm sorry. Let's fix that. I jumped ahead. From 3 to 4, -2 I heard. And then from 4 to 5, we have 1. Can you see that? Okay. There's a reason I included the endpoints and not the interior points. This is my original function, right? So right here at 1, Does it have the same slope from the left and the right? No. So that means it doesn't technically have a slope right there at 1, right? Same thing here. Does it have the same left and right slope? No. Same thing here and here. However, leading up to this endpoint, does it have the same consistent slope? Yeah. So that's why I include it here. And leading up to this, we're good. Okay, so that's why I write it out that way. That's important. Okay, so you are going to have places where you have to express the derivative. And if it doesn't have a derivative at the point, it's going to be kind of like an open circle. We'll see. Yeah. Yeah. Well, because the derivative, what is the definition of derivative? It's the slope, which is the limit as h approaches 0. Everything we do in calculus is based on limits ultimately.
If 0 to 1 is 3 and 1 to 3 is also 3, would there be
If it was the same slope from the left and right,
or wait, would it just be like 0 to 3 if it was always slope?
it would just be from 0 to 3. Okay, here's what we're going to do. These are all constants, aren't they? Right? These are all constants. So that means I'm going to draw a series of horizontal line segments. Okay, so from 0 to 1, my slope was 3. So from 0 to 1, so I'm going to start with a closed circle at 0, 3. And I'm going to go over with a horizontal line segment until we get to 1, and I'm going to leave that an open circle. Because from 1 to 3, what's my slope? 0. So now we're down on the x-axis. So I'm going to go from 1 to 3. Both of those are open circles. Okay. 3 to 4. Now I'm going down to -2. So I put open circles there as well. And finally from 4 to 5. I'm going to go to 1, and I'm going to just have that endpoint as a closed circle. So when I have the derivative, I can say, oh, what's the slope, or what's the slope when x equals 2? Oh, it's 0, because that's the value here. What's the slope when x equals 3.5? It's -2, without even looking at the original, right?
So
Yeah.
is that the whole point of these graphs? Is to be
Yep.
able to look at it like?
That's it.
Okay.
Yeah. And then we'll have applications to it later.
Okay.
That's the real fun stuff. Okay, Maya.
Okay. Why is it horizontal lines if the derivative is the tangent of this?
It's not always going to be horizontal lines. That's why I have the next example. But are these, is the slope changing, or is it staying constant? Stays constant until, and then here,
Then it would be
there we go. Okay, now we got a curve. Okay, here we go. This is going to be our f of x, and this is going to be our f prime of x. Now, we can't get an exact derivative yet. We haven't learned how to do that, but we can approximate. Okay, so here's how we're going to do it. We're going to take certain values. So let's say let's start off at the beginning, at x equals 0. Okay, I'll take this weird looking ruler and I'll put a tangent at 0. What do you think? What do you think that slope, like, you see what I mean? Just touching, what do you think that slope looks like? Just approximate.
0.2.
It's steep, it's gotta be bigger than 1, right? Like maybe, I would go with like 4 or 5. Because like 2 would be like this, right? Up 2 over 1, it's definitely steeper than 2. What do you think? 5, we'll just, again, approximate. We'll say m is approximately, oops, not 0, it meant 5. Okay, let's pick another point that maybe will help us here. Let's look at 1. Here, so I'm going to draw little tangent slopes. What happens at 1?
It's 0.
Okay, so at x equals 1, m is, looks like almost a horizontal there. Let's pick the next one. How about at x equals 2 here? What do you think? 2 is like that, maybe? Can you see it? What do you think m is approximately? Well, now it's a negative slope, isn't it? Kind of looks like almost just -1, right? So I'll just do -1. And then it looks like at 3, 0.5. We got another, again, approximate. Doesn't have to be perfect. M, because at the end of the day, we'll all have a very similar result for the derivative slope. Oh, 2.5, thank you. 2.5 is 0. Let's just do one more. I don't know. We'll stop at 3. What do you think? At x equals 3, what do you think our approximation is? What do you think? It's not quite as steep as it was at 0, so maybe instead of 4, maybe it's 2 or 3. Again, makes no difference. Pick one. 3. Okay. Now, these are not horizontal line segments. What we're going to do is we are literally going to plot these x comma y. So at 0, my y value is 5. So put a point at 0, 5. At 1, remember what I said, the slopes, all these m's, those are our y values on the derivative graph. So 1 comma 0, put a point. You kind of see what I'm doing here? 2, negative 1.
Does it matter if it's an open circle?
These are going to be all closed, and I'll explain why. 2.5, I get 0. And 3, I get 3. Okay, so now what I'm going to do is connect them with a smooth curve as best you can. It doesn't have to be perfect. Kind of looks like a parabola. Okay, and it might continue. We don't know what happens after 0. It could continue like that. No matter what, even if you got slightly different answers, maybe you got 0.6 for the first one or 0.4, every one of us would have gotten a parabola shape, okay? And it would have dipped below the x-axis because we definitely had 2 horizontal tangents and we had a negative slope at some point. Now, why did I use closed circles? It has to do with this didn't have any corners to it, didn't have any sharp edges. It had a nice smooth curve. When that's the case, not always, but almost always, you will have a nice smooth curve for your derivative graph. Okay, Mayan?
I don't know if I'm getting ahead here, but why does it look like that?
Getting a little ahead, but I will go back to this one real quickly. Oh, no, not this one. This one. You see x cubed?
Oh, 3x squared is the
3x squared. So anything that has a cubic function, its derivative graph will be a parabola.
What does that even tell us?
It tells us so much, Molly. I just can't get into it now. I won't finish the lesson. I know, and I really want to finish because you will have so much fun with this homework. Okay. So you see this graph? This is a cubic function. It's got 2 turns. My result should look like a parabola.
Is it always 1 degree less?
It will be if it's a polynomial. Jumping ahead, jumping ahead. Okay. Okay, next one. I want you to work backwards. Oh, come on. This is the derivative. Now, come on, tell me you're not having a little fun. This is kind of fun, right? Nice way to end a Friday. I mean, I know you still have one more class, but you know. Okay. What do we have here? We have 2. Remember that first graph that we did? We had our result were line segments. Here, what do I have? Line segments. I'm going to work backwards. Okay. What's the value here? So from -4 to 0, what's my slope? No, you said it right. -1, right? What's the actual value? So we're looking at the actual y value and interpreting that to slope of my original graph. And then from 0, notice I'm not including the 0. Do you see why? There's no closed circle, but we're going to assume that that unless I draw a clear open circle, we're going to assume it's a closed, okay? So now, until we get to 4, what is my slope? 3. Okay. Now, What's that mean? I'm going to have a V shape. It's kind of going to look like an absolute value function. So at 0, I have basically from -4 to 0, I have a slope of -1. Okay, mine's off a little bit, but you get the idea, right? And then at 0, I have a slope of 3, so now I'm going to go up. So it's going to just be like a little steeper here. So right here, it's going to be a closed circle. Here's why I need to have what's called a continuous graph in order to find a derivative. I wouldn't be able to find the derivative if there was an open circle here. It wouldn't make sense. So that's why we do it that way. Yeah.
Could we have picked any y value for 0?
Good question. Yes.
Okay.
I happened to just start at 0 because I didn't want to overcomplicate things.
Yeah, because the
But-
derivative function, like graph still would have worked. no
So
matter what.
I chose for you because I didn't want to overcomplicate it. I chose to start at 0, 0. Could we have started at 0, 2 or 0, -3? Absolutely. Will it have that same shape at the end? Yes. We'll get into that later. Another jump ahead.
Isn't it just easier to start 0,
It is. That's why I chose it for you.
0?
Okay, let's see. We have, how many, do we have 10 minutes? Ooh, okay. It's all good. It's fine, it's fine. It's good. We're good. We're good. This is where we want to look at, so exactly what we were just talking about, one-sided derivatives. Okay, when the left side and the right side are equal, then you have a derivative at that point. Okay, so this is where we go back to the h approaches 0. When we do, now you could do the alternative one, but I'd like you to stick with this one. So this is the right-hand derivative, so it's just h approaching 0 from the right. This is our left hand. When these are equal to each other, that means it has a derivative at that point. So remember when we were doing that first, had this line segment and then went this way and then went down and then, okay, so did it have the same left and right hand derivatives at those little corner points? No, so that's why we say it didn't have a derivative at that point, which is why when we did the derivative graph, we made a little open circle. Good? Okay. Last page. Okay, these are just really quick examples of all the stuff we were just talking about. Notice absolute value does not, because the derivative from the left is -1, right? And the derivative from the right is +1. So since these are not equal, we say it is not differentiable at x equals 0. Now, what if I said a different value? What if I said, is it differentiable at x equals 3? Well, right here is 3. Does it have the same derivative? Yeah, it has a slope of 1 here, has a slope of 1 here. So it just so happens this is the only point where it's not differentiable. But all the other places on that graph it will be. Yeah, Maya.
You would be given a graph of this, right? It wouldn't be, you'd have to find.
Well, I'm going to show you the next lesson.
Okay, so
Everybody's jumping ahead. We'll get to it. Don't worry. We have like this differentiability. How might it fail to exist? I'm going to walk you through. You'll be able to see graphically, but also algebraically. Right now, we're still kind of on the limit stuff, so bear with me. We'll get there. So here, this is an example where the derivative from the left, and I didn't do all the algebra there, but you can show it if you want. The derivative from the left is approaching a horizontal tangent. The derivative from the right is approaching 0, a horizontal tangent. So therefore, these are equal, so we know it's differentiable.
So derivative is really just slope.
Derivatives are slopes.
So why do we call it something else?
Because there's so much more to derivatives.
Like what, Miss Casey?
I said if I got all into it, we wouldn't finish. What is all this stuff referring back to? Do you remember what I talked about with speed, velocity, rates of change? That's what derivatives are, and that's how we'll apply it. It's so much fun. I love calculus. Okay. I haven't taught the AB in a while, so I just love it. It's so much fun. Okay, let's do this. Let's show that it does not have a derivative at x equals 0. So here's what I'm going to do. I know it says y, but I'm going to use f of x so you can kind of see. So f prime of 0 from the left. So I'm going to put a little negative sign. That's going to be the limit as h approaches 0 from the left. What am I? So I'm going back to that x plus h1 minus the f of it. So if I'm approaching it from the left, I'm plugging it into x squared. So that's going to be x plus h squared minus, anybody? X squared all over h. Okay, let's go ahead and do that real quickly. So we have x squared plus 2xh minus, or sorry, plus h squared minus x squared. Again, I know some of you just want to cancel the h. I do like shortcuts, but factoring is something I will always do in this case to avoid making a mistake. Sorry if I'm going a little quickly. I just want to make sure we have time to finish. What do we get? 0. Oh, 2x, and then, yeah, plug in 0. So that's going to be 0. Okay. Well, we just, yeah.
Why do we plug in?
Oh, because it's f prime of 0, so that's our x value. I could have put, if you wanted to, I could have put 0 in all these spots, and that would have saved us some time. What's that, Molly? I hear you. You could have plugged in 0 from the start. I just wanted to show you, right? We really get 2x here. So then that means f prime of 0 from the left means I'm substituting in 0 there to get 0. Okay, that's the left-hand limit. The right-hand limit. I'm not even going to do the limit. Why? No. That's an equation of a line. Okay, if it's an equation of a line, can't we just look at it and say, what's the slope here? 2. Yeah, you can. So I'm going to tell you, if you have the equation of a line, I don't need to see that whole limit business. Okay? If you want to do it, fine. But I don't need you. Well, all I'm going to do here is I'm going to write f prime of 0 from the right is equal to 2. So, therefore, the function does not have a limit as 0.
Wait, but why don't you plug in 0?
There's because it's a constant, there's nothing really to substitute in for. See, this one ended up being 2x, so when I plug in 0, I got 0. This one, if I were to run through this whole business, I wouldn't end up with an x to substitute in for. It just works out to be 2. So this does not have a derivative at x equals 0. Okay, we got a minute to answer any questions.
Can you use